Alright, so today I'm going to be going through the final exam from spring 2023 for AAE 204. Let's go ahead and jump right in. For problem 1, we have consider the tip-loaded cantilever beam of length L shown in the figure below. The elastic modulus is E and the cross-sectional moment of inertia is I. Then for part A, we have integrate the internal bending moment to find an expression for the deflection of the beam. Clearly state the differential equation and the boundary conditions that you are using. And then for part B, we have, without performing any calculations, describe in words how you would solve for the deflection if the discrete tip load P was replaced with a distributed load Q of X over the entire length of the beam. Write no more than 3 complete sentences. Alright, so what is the problem asking for? The problem is asking for us to find the deflection of the beam. Remember that deflection is going to be the displacement of the beam in the y direction. And specifically, to find the deflection, they want us to integrate the internal bending moment. So, the differential equation we're going to be using is, of course, this one here. We have that the moment in the x is going to be equal to d squared v over dx squared times the constants e and I, v of course being the deflection. And then for our boundary conditions, we're going to have v at x equals L is going to be equal to 0, since this is the fixed end of the beam, and dv at x equals L is also going to be equal to 0, again, because this is the fixed end of the beam. These boundary conditions are going to be important later on when we're solving for the constants in the expression, but getting ahead of myself. First, of course, we need to start by actually finding what the bending moment is. So, the bending moment is going to be, if we define our coordinate system as being this, and I'm just defining my sign conventions here. So the moment is going to be this load P, and it's going to be negative since it's pointing downwards, times the distance x at any point along this beam. So m of x is just going to be equal to negative px. All right, and now we're going to just plug this in to our differential equation here. And I'm going to go ahead and move the constants e and I over this side of the equation when I write it down here, just because I like to have all of my stuff on one side. So equation here. And this is a pretty simple thing to integrate. So we're just going to integrate with respect to x on both sides of this equation. So we have all right. And I like to do this integration one at a time. Just helps me keep everything straight. So I'm going to continue this on the next page. I'll go ahead and rewrite the equation up here again at the top, just for clarity. Right, so we integrate once. integrate again. And so now we are left with our general expression. And now we just need to find what these constants C1 and C2 are, and we're going to do that by using our boundary conditions. Quick reminder that our boundary conditions are b at x equals L. X equals L being the fixed end is going to be 0. Since it's fixed, there's no displacement. And the slope of the displacement, dv over dx, is also going to be 0 here. And you can see doing the integration separately, like one step at a time, is also going to be helpful for this step because we already have what dv over dx is going to be. So we have that dv over dx at x equals L is going to be equal to 1 over EI of negative PL squared over 2 plus C1 and this is going to mean that C1 is just going to be equal to PL squared over 2. Okay, and now we can plug that back in to our very first equation in order to find what C2 is going to be. So we're going to have at V x equals L 0 equals 1 over EI times negative P L cubed over 6 plus PL squared over 2 times L plus C2. Because remember that this term here is equal to C1x. All right. So we're going to have 0 is equal to 1 over EI times negative PL cubed over 6 plus PL cubed over 2 plus C2. And if we solve this out, we end up with C2 is going to be equal to negative PL cubed over 3. So our overall expression for the deflection of the beam is going to be 1 over EI times negative px cubed over 6 plus PL squared over 2 times x minus PL cubed over 3. And here's our final answer. And part 2 of this problem. They want us to describe in words how we would solve for the deflection if the discrete tip load P was replaced with the distributed load Q of x over the entire length of the beam. So if we had some distribution of load q of x over the entire length of the beam. And I'm not saying it would look like this, it's just an example. Now, there are a couple different ways you can answer this question. You can, of course, go with the tried and true method of find the reaction forces and then finding the shear and then the bending moment, which, side note, I skipped finding the reaction forces, like solving it out on paper at the beginning of this. I probably shouldn't have, but it wasn't necessarily necessary for this problem. Necessarily necessary, huh? That's kind of funny. But because if we were finding the internal bending moment, so if I took the cross section of this beam and we were going from x equals 0 to x equals L, we take the infinitesimally cross section of the beam, you can see that the reaction force at the end of this beam isn't really a part of this. But if I were to find the reaction force, it would simply be P in the Y. But anyway, so yeah. So one way you can do this, find the reaction force, then find the shear and bending moment equations. From that, and then you just integrate them as we did before. You just have more powers of x. The other way you can do that is you can actually go ahead and start with the differential equation EI d to the fourth x over dx to the fourth equals negative q of x. And you can actually just integrate this equation directly, which this is probably the way that I would do it, just because I find this method more straightforward. But as long as you can prove that you know how you would solve the problem, you'd be fine if you got a question like this. So it's the end of problem 1. Alrighty, on to problem 2. A damaged wing skin is repaired using duct tape with a yield stress of 35 megapascals. The wing skin experiences the plane stress state shown on the right. We've got our stress state here. Part A. Calculate the principal stresses and maximum shear stress in the wing skin. Part B. Sketch Moore's circle for the stress state in the wing and determine the principal angles theta P1 and theta P2 relative to the current stress state. And then part C. Using your answers to A and B, state whether the duct tape works as a provisional repair method for the damaged wing skin. Alright, so what is it asking for? Problem's asking for the principal stress and the maximum shear stress. They want us to draw a Moore's circle and find the principal angles and determine whether or not this yield stress up, and basically determine whether or not it will exceed the yield stress and the duct tape shall fail. So for part A, we have calculating the principal stresses, which we can do using this quick equation for sigma x, sigma y over 2. Sorry, that should be minus the square root of sigma x minus sigma y over 2, and that whole term squared, plus tau xy squared. You might also recognize this formula in the form theta average plus minus tau max, but we'll stick with this one for now. First, let's make sure we know what sigma x, sigma y, and tau xy are. So sigma x, we have positive 20 megapascals as denoted by our coordinate frame. Sigma y is 25 positive. And then tau xy is 10. Okay, so we can just plug those values in to our equation here to solve for the principal stresses. And you can just plug this directly to your calculator. And you should end up with sigma 1 as being 32.8078 megapascals, and sigma 2 being 12.1922 megapascals. Sigma 1 is always going to be the one that is algebraically greater than sigma 2, just if you're wondering which is which. All right, and then we can get tau max by simply taking sigma 1 minus sigma 2 over 2. And if we do that, we end up with 10.3078 megapascals. Okay, and we have our principal stresses and our maximum shear stress. So that's part A. You can also find tau max by using this term up here, but since we already have the principal stresses, might as well use them. All right. Alrighty, on to part B. Creating our Mohr circle. So let's go ahead and start by sketching out our axes. Remember that positive shear is going to be on the downwards axis, and then of course positive sigma is going to be to the right. I like to start by finding the midpoint of the circle, which is equal to sigma average, which is going to be sigma x plus sigma y over 2, which of course is going to be equal to 22.5 megapascals. So this point here is going to be 22.5. And then we'll plot our two stress points. So we have our point A is going to be the x. So it's going to be the point 20, 10. And then if we come 180 degrees around, right across from it, we're going to have the y, which is going to be 25, and we're going to represent it as negative 10 for the shear. We'll draw a line through those, and then we'll draw our circle, which is kind of circle shaped. As you can see, I am a fantastic artist. And of course, the radius of the circle is simply going to be equal to tau max, which we determined to be 10.3078 in the previous part of the problem. All right, Now we just need to find our principal angles. So we can use the formula sine 2 theta p1 is equal to tau max, not tau max, it would be tau xy over the radius. So we're going to take the inverse sine of tau xy over r in order to get 2 theta p1, except you have to remember the inverse sine function on your calculator only goes from 90 to negative 90. So it's actually going to end up giving you this angle here. So you'll have to subtract your inverse sine function from 180 degrees in order to get what 2 theta p1 actually is. So we're going to take the inverse sine of tau xy over r, which is going to give us 75.96296. We'll go ahead and do all of the sig figs, subtract that from 180 in order to get 2 theta p1 as being 104.0370 degrees, and that gives us our first principal angle of 52.0185 degrees. All right, now sigma p2 is, sorry, not sigma, theta. I just realized that when I draw my sigmas and my thetas, they look a little too similar. Anyways, so now we just have to find sigma p2. I did it again. I'm so sorry. But we can simply find sigma p2 by adding 90 degrees to theta p1. We are left with 142.0185 degrees for principal angle 2. And remember that this is going to be the angle between the x-axis and the principal stress plane in the y, which is of course going to be perpendicular to the principal stress plane in the x, which is why we were able to just add 90 degrees to the first principal angle. All right, that's part 2 done. Now on to part C. Quick reminder, part C, they wanted us to determine whether or not the duct tape would work as a provisional repair method based on our answers obtained in parts A and B. So because the maximum normal stress and the maximum shear stress never exceed the stated yield stress of 35 megapascals, and they didn't specify whether the yield stress was shear or normal, but as neither of them exceed, I suppose it doesn't really matter. Reminder that sigma max is going to be equal to the principal stress 1, which was 32.8. So, in short, yes, the duct tape will work as a provisional repair method.
All right, let's move on to problem 3. Consider a simply supported beam of length L with a force P applied at x equals L over 2 as shown in the figure below. The elastic modulus is E and the cross-sectional moment of inertia is I. Our beam. Then part A. Use Castigliano's theorem to find the downward deflection at x equals L over 2. And for part B, without performing any calculations, describe in words how you would find the deflection of the above beam at x equals L over 4 using Castigliano's theorem. Write no more than 3 complete sentences. Alright, so what is the problem asking for? It's asking us to find the deflection at the point x equals L over 2, conveniently where our load is being applied, and they want us to use Castigliano's theorem. A reminder that Castigliano's theorem determines the deflection by finding the strain energy and then taking the partial derivative of that with respect to P in order to find the deflection at a point under load. It is specifically a point where a load is being applied. So let's go ahead and start by first finding our reaction forces at the supports, because we have to find the bending moments first. So sum of forces is going to be 0. We have I'm going to label this point A and this point B. So we have RA plus RB plus R load, which is going to be P, and it's downward. I'm defining up as positive, Y is negative, up is positive, down is negative. That's going to be equal to 0. So we have our first equation is going to be this, and then we have the sum of moments, and I'm going to take the moments about point A. So the sum of the moments about point A is going to be RA times 0 minus P times L over 2 plus RB times L, and that's going to be equal to 0. So we're going to have RB times L as equal to P L over 2. So that means that RB is going to be equal to P over 2, and thus RA is also going to be equal to P over 2. So our beam is symmetrically loaded, and since we have a constant modulus and a constant moment of inertia, that means that our beam is completely symmetric, so we only have to find the strain energy on the left half, because normally what you do is, depending on where your point was being applied, you'd find the strain energy in like the left side and the right side respectively from the point at which the load is being applied. But since this is symmetric, we only have to analyze the left-hand side. So the moments on the left-hand side are going to be equal to RA times X, which is going to be equal to P over 2 times X. As you can see, if we take our cross-section, some distance X away from point A, you can see the only thing we have acting on it is the reaction force, and thus the moment is going to be P2 times X. Now, we're going to calculate the strain energy by using the Castigliano's theorem. So we have the strain energy as being the moment squared over 2 times EI, and then dx. So in order to find the total of strain energy, I'm going to take this twice, and I'm going to take it from 0 to L over 2, and it's going to be 1 over 2 EI, and then the moment squared is going to be px over 2, and then that whole term is going to be squared, and then it's going to be dx. So if we solve this integral out, we're going to end up with I like to go ahead and kind of separate out all of the integral terms, but you end up with 1 over EI times P squared L cubed over 12. Okay, so here is our strain energy equation. And now, to use Castigliano's theorem, we're going to take, in order to find the deflection is going to be equal to the partial derivative of u with respect to p. So it's going to be p squared L cubed 12EI, and then if we take the partial derivative of this with respect to p, we end up with PL cubed over 6EI. And this is what our deflection equation is. Alrighty, now on to part 2 of this problem. Without performing any calculations, describe in words how you would find the deflection of the above beam at x equals L over 4 using Castigliano's theorem. Write no more than 3 complete sentences. Alright, so finding the deflection at x equals L over 4 is a little bit trickier, mainly because we're going to have to apply a fictitious load at x equals L over 4. The reason we have to do this is Castigliano's theorem only applies for a point at which a load is being directly applied. So in order to get around that, we have to apply a fictional load. Call that Q at x equals L over 4. It's also going to make our integrals a little bit more tricky because now we're going to have to find 3 different bending moments. One in this section, one in this section, and one in this section, because the bending moments in each of these 3 sections are going to be different equations. So, solving for the deflection. We would, of course, first solve for the internal bending moments. In each of our 3 sections. Again, applying fictional load Q at x equals L over 4. And then we can find the strain energy in each of our 3 sections individually. So we would have and then you just have to add them together and then take the partial derivative with respect to load, and of course we would plug in 0 for our fictitious load Q because it was kind of just there as a placeholder so we could actually use the Castigliano theorem. Alrighty, and that is a brief overview of how you would solve this problem if they asked you to find the deflection at x equals L over 4.
Alrighty, and on to the last problem. So, problem 4. The column of length L equals 5 meters is shown below, made of a material with an elastic modulus of E equals 70 gigapascals. The cross-section is rectangular, with dimensions base equals 80 millimeters and height equals 120 millimeters, and the XY coordinate system shown as located at the centroid of the cross-section. So here's our column. You can see that it is pinned up at the top, and we have our cross-section. So for part A, we have calculate IY and IZ for the cross-section of the column. Then for part B, we have calculate the critical buckling load for the column. And then for part C, we have without performing any calculations, describe in words how the critical buckling load of the column will change if the pin support at the top is removed. Write no more than 3 complete sentences. All right, so let's go ahead and start by calculating IY and IZ, which are going to be the moments of inertia for the cross section. Quick reminder that the formula for the moment of inertia of a rectangle is going to be 1 over 12 base times height cubed, just like in general. So we can calculate IY as being 1 over 12 BH cubed, which is going to be equal to, and I like to just stick with everything in meters just so I know all of my units will work out at the very end, but we end up with 1.152 times 10 to the negative 5th meters, right? And then we can do the same thing for IZ, except for your base and height, it's going to be flipped, so it's going to be 112 h times b cubed, because we're taking the moment of inertia with respect to the z-axis. So it's going to be 0.120 times 0.080 cubed, and that's going to be 5.12 times 10 to the negative 6th meters to the 4th, and that should be meters to the 4th. Alrighty, so that's part A of this problem. Now for part B, we have to calculate the critical buckling load for the column. So the formula for critical buckling load is given for a column that is pinned at both ends. Is going to be P critical is going to be equal to pi squared times EI over L squared. So let's go ahead and calculate it out for both IY and IZ. The critical buckling load for the column is going to be the smaller of those two values. You might recognize that since the IZ moment of inertia is smaller than the IY, that the critical buckling load will be the IZ one since it's going to be smaller, but I'll go ahead and do both of them out because it can't hurt. So we're going to have PCR is equal to pi squared times 70 times 10 to the 9th PA times 1.152 times 10 to the negative 5th meters to the 4th over 5 meters squared, and that's going to give us a value of 368,354 newtons. Sorry, that's not right. That was a 1. 18,354 newtons, or 318.354 kilonewtons. And now we just have to do the same thing for IZ. So pi squared times 70 times 10 to the 9th pascals times 5.12 times 10 to the negative 6th meters to the 4th over 5 meters, all that squared. And you're going to end up with 141.491 kilonewtons. All right, so like I said, the smaller of the two is going to be the critical buckling load. So PCR for column is going to be 141.491 kilonewtons. All right, now for part C of this problem. Without performing any calculations, describe in words how the critical buckling load of the column will change if the pin support at the top is removed. Write no more than 3 complete sentences. I mean, we wanted to go really short and sweet answer. It's going to be smaller, which, I mean, kind of makes sense intuitively, right? Like if you remove the support at one of the ends and then you start, loading it, it's probably going to bend a little bit quicker if the other end isn't fixed. But I will also show you why it works sort of show you why it works mathematically, because I mean, I'm not going to run through like the entire derivation for the equation, but basically, if the pin support at the top is removed, so if the formula for critical buckling for a column with one fixed and one free end the formula is going to be P star is going to be equal to pi squared E I over 4L squared. So we can even be really specific. You can see that the critical buckling load is going to be reduced by a factor of 4 if you remove the pin support at the end. Right, and that concludes the spring 2023 final exam.